Welcome back everyone, Houston Math Prep here doing an examples video on second order linear homogeneous equations with constant coefficients. So if we start with ay double prime plus by prime plus cy equals 0 and a, b, and c are constants only, then we can convert this second order differential equation into what we call the characteristic polynomial am squared plus bm plus c based on the a, b, and c here in the original differential equation. We'll then solve this quadratic equation using some algebra, so usually we'll factor or use quadratic formula, maybe use completing the square. And in this example video, we're talking about when we get distinct real roots for our solutions to this characteristic polynomial. So we get some solutions m1 and m2. And if these are two distinct real numbers, one of our solutions, remember, will be y equals e to the m1 times x, where m1 is just some solution, so it'd be some constant multiple of x inside our exponential. That will be some solution, and it also means that y equals e to the m2 times x will also be a solution to our equation. We will think of both of these exponentials as our fundamental solution set, and our general solution for this differential equation will be y equals some constant times e to the m1x plus some constant times e to the m2x. And now we'll just solve several examples with you. So here we've got y double prime minus 3y prime minus 18y equals 0, homogeneous, linear, constant coefficients. Our coefficients, a is 1 here, b is negative 3, and c is negative 18. So our characteristic polynomial is going to look like 1m squared, just m squared, minus 3m minus 18 equal to 0. We solve this for m. This actually factors, so in this case we'll get m minus 6 times m plus 3 equal to 0. Once we have our factors equal to 0, remember, set each factor equal to 0 and solve. So we'll get m minus 6 is 0. We'll get m plus 3 is equal to 0. If I add 6 to both sides here, I get my first m value is 6. Over here, subtracting 3 on both sides, I get my second m value is negative 3. So I know my fundamental set of solutions are exponentials with these as the constant multiples inside. So our solution is going to be c1, some constant multiple of e to the 6x, plus some constant multiple, c2, of e to the negative 3x. So again, my m1 and my m2 are just the multiples of x inside of the exponential functions here. Looking at our next one here, 2y double prime minus 3y prime minus 2y equals 0. So our characteristic polynomial for this equation is going to be 2m squared minus 3m minus 2, and that would be equal to 0. We'll solve for m here. This one also solves by factoring, so we'll get 2m plus 1 times m minus 2 equal to 0 if we factor this. So you need to be good at your factoring, obviously, to do these constant coefficient equations here. So we set each factor equal to 0, so 2m plus 1 equals 0, and m minus 2 equals 0. If we subtract 1 and divide by 2, we'll get that our m1 is negative 1/2, and here if we just add 2 to both sides, we'll get our second m value is 2. So our general solution based on those m values, y is going to equal c1 e to the negative 1/2 x, also known as negative x over 2, plus some constant c2 times e to the 2x. Looking at our next one, y double prime minus 5y prime equals 0. So you'll notice we have no c term here. Our a is 1 in this case, our b is negative 5, c is actually 0. So our characteristic polynomial here is going to be m squared minus 5m equal to 0. This is easily factored. We actually just factor out a greatest common factor of m, so we get m times m minus 5 equal to 0. Setting each of those factors equal to 0, the first one solves itself. We just get m equals 0. The second one, m minus 5 equals 0. We'll have to actually add 5. So here our m1 is 0. This one, when we add 5 to both sides, we'll get that m2 is equal to 5. So with 0 and 5 as our solutions, think about what that would say. That would say y equals c1 e to the 0x plus c2 e to the 5x. Now, do we want to leave this answer as it is? No, of course not. What is e to the 0x? That would just be e to the 0. And what is e to the 0? Well, it's just 1, right? So really this just becomes c1 plus c2 e to the 5x. Much better manners mathematically to write it that way, yes? Looking at our next one here, y double prime minus 16y equals 0, you notice we have no y prime term. So this is actually a is 1 here, and b is 0. C is negative 16. So our characteristic polynomial here is actually m squared minus 16 is equal to 0. You can factor this if you want. We'll go ahead and solve by square root. So adding 16 to both sides, we'd get m squared is equal to 16. That would give us that m is positive or negative 4. So think about what that's really saying. That's saying that m1 is positive 4 and m2 is negative 4, or vice versa, right? But you have positive 4 and negative 4. So your answer for this second order equation is going to be c1 e to the 4x plus c2 e to the negative 4x. And looking at our last one here, y double prime minus 3y equals 0. So again, you can see no y prime term tells us b is 0. In this case, a is 1, b is 0, and now c is negative 3. So we get a characteristic polynomial of m squared minus 3 equal to 0. Just like the last one, I'll go ahead and add to the other sides. We'll say m squared would equal positive 3. And taking the square root of both sides, we would get that m is equal to plus or minus the square root of 3. Remember, that tells us actually two distinct m values, right? So that tells us the first m value is positive root 3, and that tells us the other m value is negative root 3. If we go ahead and write our solution based on those, then we'll get that y is equal to some constant multiple of e to the square root 3x plus some constant multiple of e to the negative root 3x. All right, we've got two more videos, one on repeated real roots, one on complex conjugate roots for the characteristic polynomial, and solving the second order equations with constant coefficients. Thanks for watching, everybody. We'll see you in the next video.